Hi everyone, and welcome to this presentation. Today, me and Penny are going to talk about some ARM feature that we investigated, and we will aim to supporting Xen in the future. Yeah, for sure, I have to click. Okay, cool. So all of these hardware feature helps the software to improve security and performances. And talking about performance, we can start with SVE. So SVE stands for Scalable Vector Extension, and this feature introduces new instruction and registers that can improve performances on vector computation, but also loop optimization. Those registers are quite big. They start from 128 bits up to 2048. And the vector length is set by the CPU architect, but it can be modified by the operating system or the hypervisor. A nice thing about SVE is that the code can be built just once and it can run across multiple platforms, and because it can scale automatically across all vector length without recompiling. So here on the right, we can see a function that can benefit from SVE, and we can see why. The function you can use with SVE less instruction, and also the new instruction that can be used with this feature improves performances. So we think that application might want to use the feature, and we would like our guests to support it. So how can we do that?
Is there a software to make this full screen?
Because to be honest, I don't know. Just minimize. Yeah, it's pretty small. I know. Make full screen. I will try. Is it better?
Definitely yes.
Okay. Cool. So how can we support this feature in Xen? We did a rough investigation about the feature, and yeah, we investigated some area of work, and we saw that since those registers are quite big, we might have some work around the context switch area, because we might want to allow or disallow some guests to use the feature because sometimes the context switch time matters. We would need also to work to present the feature to the guest using the usual feature register provided by ARM. We might need to trap the access to those registers and handle the exception, maybe for those guests that are not allowed to use this feature. So moving on, we have another nice feature that is pointer authentication. This is a security feature that is used to understand when an address is authentic or it was modified. How does it do that? This feature introduces new instruction that can compute a cryptographic hash of a pointer, starting from the pointer itself, a key, and an optional other value. And the hash is stored together with the address for a 64-bit address in the top unused bit. There are in total 5 keys to sign address pointers, data pointers, or generic pointers, and each key is composed of 2 registers of 64-bit length. 2 things to remember for those registers: that the first one is that EL0 can't access them directly, and the other one is that the registers are not banked, so it's software responsibility to save and restore them during exception level switch. So how can an application use this feature? Here on the left, we can see an example, and we are saving a return address to the stack. So what if an attacker can exploit some flaw in the function body and modify this address? Basically, the final return instruction can jump to a modified address, and we don't like that. So we can use pointer authentication to sign the address before storing it to the memory, and just before returning we can authenticate it, and if it was modified we can raise an exception, or we can make the address illegal so that the following return will throw a different kind of exception. So, but is it enough for the security of our pointers? Probably not, because another weakness comes from another class of attack called jump-oriented programming, and this kind of attack exploits the fact that the software is composed by many lines of code, libraries, so it's full of indirect branches, and the attacker can modify the software flow to glue together pieces of code. And in this particular example, an attacker can sign its own pointers, and from now on, those pointers will be fine for the processing element. So how can we address this weakness? Another feature comes to help, and it is BTI, Branch Target Identification. And this feature helps to protect indirect branches on requested memory page. So this feature is introducing a new instruction, BTI, but also a new flag in the stage 1 block and page descriptor. And this flag is used to enable or disable the feature on the memory page. So what is the idea behind the BTI? The idea is very simple. On the left, we have an indirect branch to an address that should be our function. But if this address is modified, we can jump everywhere into the code. So instead, using BTI, we can place BTI instruction right in the entry point of every function, so that every branch, if the branch doesn't land on a BTI instruction, or in some cases also a pointer authentication instruction, it will immediately throw an exception, and we are aware that something is going on. So how can we support this in Xen for our guests? We investigated that probably we will need to check that all core brought up by Xen can support the feature. We might want to have a configurable to present or hide the feature to the guests. We will need to save those keys for context switch between guests, and maybe we could trap and handle some exception for those guests that are not allowed to use this feature. Okay, so last but not least, the MTE feature. This is memory tagging extension, and this is used to mitigate buffer overrun, use after free, and other kind of memory of bugs that are popular for memory unsafe languages. This feature implements by hardware a mechanism of lock and key, where pieces of memory is tagged by a lock and the pointers are tagged with a key. So during the memory access, the instruction compares the key and the lock, and if there is a mismatch, we can raise an exception. So this feature introduces a new type of memory, the normal tagged memory, and the key for the pointer is stored together with the address in the top unused bit. So the drawback here is that this tag steals a little bit of space from pointer authentication. So let's see it in action. Here we have a simple function without MTE and with MTE. For sure, we see that MTE introduces a little bit of overhead because we have more instruction, but also an overhead in terms of memory consumption. But we think this is fine because there are other software implementation of the same technique that consumes a lot more memory, code size. They are worse in performance. So we think that application can benefit from this feature, and we would like our guests to support it. So how can we do it? Basically, also here we will need the core brought out by Xen to provide the feature. We might need a configurable to present or hide the feature. We need to save the configuration registers for MT, and we might need to handle register access and exception for those registers, maybe for those guests that are not allowed. Okay, so this was my last feature to present. Now I can leave the floor to Penny, and she will talk about the status of R64V8R. Penny, are you?
Yeah.
Can you hear?
So
Okay.
yeah, can you hear me? Yeah.
Yes.
Okay. Hi, I am Penny. Do I need to shoot the camera? Oh, I don't know how to set up it. Never mind. So I am a senior software engineer for ARM, and I will do the left talk. First of all, I would like to briefly introduce current status and what we are going to do for the AX64V8R. For the upstream work, the first stage is to successfully run a guest, no matter it is a Linux guest or a Zephy guest, on a single core AX64V8R platform. The codes will be roughly divided into two parts to deliver: system booting and VM initialization and running. And for the POC work, the first topic is about SMP enablement on AX64V8R. The major issue we are encountering here is that there is no EL3 on AX64V8R. So the legacy SMC core-based PSAI services is not going to work. Right now, we are seeking to implement a coexistence firmware in EL2 to provide PSAI services. So SMP boot could be through function core-based PSAI services. The second topic is about how to build intra-VM communication on AX64V8R. Here we refer to statically configured shared memory and event channel. Actually, the base codes for both features have already been merged into Xen 4.17. So the left work is to port them to the AX64V8R. And the main drawback here, one is that considering the scenarios on AX64V8R, how to implement a simplified Linux guest with very limited then advanced features. Right now, only shared info and event channel are needed. Another one is that the memory for shared info is special 4K pages. How to implement it with MPU memory region is becoming tricky. I will illustrate a scenario to explain why. Considering two VMs are trying to do event channel-based intra-VM communication, when one guest tries to signal another through event channel notification, it will track to EL2 through a specific hypercore and then set up calling bit in receiver's shared info as the signal, which means the notifier guest needs only EL2 memory access to receiver's guest's shared info, and only during this hypercore context. And both solutions are still under discussion in community. If you are interested, welcome to join. Next slide, please. Another feature I'd like to implement for Xen is GIC v4. Before introducing GIC v4, I will briefly talk about how interrupts are normally injected into a VM on GigWe2 or GigWe3, and why we need GigWe4 at the first place. The whole process is asynchronous, the interrupt injection. It could happen anytime, no matter whether the virtual CPU is running or not. Virtual interrupts are not always tied to the physical interrupts. If they are, the physical interrupts must be taken to the hypervisor before the injection. Next slide, please. So if you want to calculate the costs involved in injecting an interrupt, each step needs to be taken into account. From the very beginning, when a peripheral equipment emits a physical interrupt and it has been taken to the hypervisor will acknowledge it, which makes it active. Then it will find the corresponding virtual interrupt and try to insert it into the list of pending interrupts in the order of priorities. When this virtual interrupt has a sufficiently high priority in the list for a VPE and also that VPE is scheduled on a PE, the hypervisor will write this virtual pending interrupt into a list register. Now, finally, a virtual interrupt is injected into a VM. You could see that the whole process generates thousands of cycles of pure overhead on modern CPU. Let alone that sometimes when trying to inject in virtual interrupt, the VPE has not always been scheduled. Then the hypervisor might choose to reschedule it, which as a result brings more latencies. Next slide, please. To solve that, we introduce a new concept called direct injection. With direct injection, we could bypass the hypervisor and directly reach the vCPU. This new process shall provide constant latency and reduce the amount of emulation. Next slide, please. To implement this new concept, the new firmware GigWe4 has been brought up. GigWe4 is an augmented GigWe3. Actually, the major feature GigWe4 introduces is only the direct injection of the VLPI. Other than that, it will inherit all the features from GigWe3. For direct injection of VLPI, in the ITIs will have a new VPE configuration table to track all VPE's residency. That is, which redistributor a VPE will be scheduled on. There are also two new virtual tables for VLPIs, per VPE pending tables and per VM configuration table. There are also a few updates on the III patch. The new distributor could track residency of VPE now, and the new CPU interface is allowing seamless injection. Next slide, please. Before introducing doorbells, I'd like to talk about VPE's two states from the geek point of view, resident and non-resident, and how they are resulting doorbell. A VPE is resident on a redistributor means the VPE is scheduled in, and gig R vpend base R holds its VLPI pending tables. Gig R vprop base R holds its VLPI property tables. Also, only in such state VLPIs could be directly injected to the VPE. On the contrary, non-resident means the VPE is scheduled out. Then, when the interrupt arrives, GigWe4 hardware provides a new mechanism to notify. That is doorbell. So what is a doorbell? It is a physical LPI which hardware automatically emits to indicate that a VLPI is pending. It will only get delivered if the target VPE is not resident. Next slide, please. Actually, after putting GigWe4 in production, we encountered a few drawbacks. One aspect is that the gig states do not really match the VPE state. Previously, we talked about two states from the gig point of view, resident and non-resident. However, from VM point of view, VPE has another state called block state. Block state shall be viewed as non-resident, so it also forces the delivery of doorbell. Hypervisor should enable doorbell when VPE entering block state. For example, VPE is running a WFI in guest mode, and hypervisor shall disable the doorbell on leaving it. Such state transition, switching in, switching from the block state, will occur frequently at runtime, which means that we need to frequently reconfigure the doorbell. We have been doing the math. Up to 6 comments, ITS comments, are required to each week at most, which means it will send the cost of a WFI to the roof. Also, we found that in actual implementation, we use vmapti to initialize doorbell configuration. Since vmapti command is to initialize the VLPI, which indicates the doorbells are per VLPI, but it shall be per VPE in theory. Another fact is that GIC-v4 makes a point in always having the half information at the place. The ITS knows about the VLPI mapping, the doorbell, the target redistributor, but not the virtual tables, the virtual property table, and the virtual pending tables. On the contrary, the redistributor only knows about the virtual tables, and only when the VPE is resident. The fact that they both don't know the whole info leads us to a lot overhead for communication on runtime on sharing info. Next slide, please. So in order to fix above issues we have encountered in production, GIC-v 4.1 is introduced. I am not going to talk too much details about it. It is another big topic. Only a taster here. So in GIC-v 4.1, redistributors and ITS are both updated. Right now, redistributors are going to be aware of all VPEs, all related info all the time. There will be shared memory between redistributor and ITS to pull it through. There is a new doorbell interrupt type, default doorbell interrupt. It is going to be per VPE as expected. Fast and simple doorbell invalidation reconfiguration will be introduced for cheaper WFI entry and exit. The last and definitely not the least, newly implemented direct virtual SGI injection will save a lot on IPI communication. Next slide, please. The last feature I'd like to introduce is Realm. It is actually a very fresh new feature. Realms are protected execution environments that are provided by ARM CCA, ARM Confidential Compute Architecture. And the hardware architecture of ARM CCA is called Realm Management Extension. It is an extension to the ARM v9 Amplifier architecture. Seen from the picture, other than the traditional normal non-secure and secure world, RME brings us to the full world scene with 2 additional security states, root and realm. Along with that, we also have 2 new additional physical address space, realm and root physical address space. With realm, second parties users could do confidential compute. A realm normally contains both a user EL0 application and an EL1 kernel space. Non-secure hypervisor like Xen, as the higher privileged entity, will still retain the responsibility for allocating and managing the resource utilized by realms, but cannot access their contents anymore. Next slide, please. Trust Room is the legacy. Compared with the legacy you can see from the right bottom picture, explains how we transition from the traditional 2 words to the newly 4 words scene. Apart from that, IME also adds the following features. the ability to dynamically transition memory granules between physical address space and granule protection check. In the new system, all physical memory is divided into granules. When an agent attempts to access a granule, the access is subject to granule protection check. The requested physical address space is checked against the assigned physical address space. If they match, the access is permitted. If not, violation results in a granule protection fault. The left bottom picture shows the matching relation in details. You can see. Next slide, please. So how Xen will affect hypervisor like Xen? Like I said before, non-secure hypervisor cannot access realm VM memory directly, cannot access realm VM GPFP system register and other registers belonging to PE directly. But realm VM still need non-secure hypervisor to handle some traps, like MMIO emulation with GIC and SMC, etc. So aside of carefully designed software components, Realm Management Monitor RMM, Realm Management Interface RMI, and Realm Service Interface RSI have been brought up to guarantee the confidentiality and integrity for Realm data and provide enough information for hypervisor to implement above. Here is an example for better understanding. On first entry to a realm vCPU, PE state should be initialized according to section PE state or reside to AX64 state in ARM architecture reference manual. These registers are not going to be written by Xen directly anymore. Xen needs to write the value into a data structure named realm execution context and sends it to RMM through RMM interface. Then later, RMM will restore this realm register from REC on realm creation. That's all. Thank you. Thanks for the listening.
Okay, I think we have a question from Ian.
Yeah, there was an understanding question of one of the earlier
Okay,
slides.
we can go back.
I'm an x86 person, and over time I've heard a number of ARM acronyms, but what PE is did not become obvious.
Yes, it is a processing element, PE. You mean PE?
Okay, so is this a hardware construct or a hardware term or a software term, meaning an analog of the vCPU? Sorry?
That's on an analog CPU.
Yes.
That's a processing element, which means a set of register and context at tier 1 level. So you can see it as a CPU or a CPU.
Okay.
A PE is a running vCPU. That's a currently running element, where the VP is a virtual one which can be running or not running. So it's just an acronym coming from the hardware manual.
Yeah. It wasn't entirely clear whether there would be such an association.
We tend to use this word in presentation where we should use CPU, vCPU, that would be more for
I think so.
Okay, maybe you need to clear up to 20 for the question because you will not understand what is going on. Penny, can you hear us?
Actually, I cannot hear very clearly. It's about VP equals to vCPU or something like that.
Just that we answer the question.
Yeah, something like that. But we answered the question, so everything is fine. Okay.
And then I have also a question to your part of the presentation, where for all of the features you basically explicitly mentioned that they will need exposure at the VXL level. And my question is, on the ARM side, do you not have a general mechanism which basically makes this implicit already, like we have with CPU ID on x86?
Yeah, basically, so
we
have a feature.
Whenever we add a new feature, it goes without saying that it needs exposing in a way, or effectively, there needs to be a way to hide the feature, because if it's not there, there's nothing to expose.
Yeah. Basically, yes. What I meant is we need to basically trap this register and provide the feature to the guests that are allowed or not to the guests that are not allowed.
Yeah, I mean, since you mentioned individually on every of the features, um, the the mechanism that you have for this in LinuxL is a generic one, or is one where you add a new guest config option for every feature?
We will add a guest specific
Yeah.
an option for each feature.
Yeah.
Okay, and that is what I would recommend again.
So reason for that is for some of those features. So let's take the example. Depending on your hardware architecture, the cost on the context switch of the SV feature might be huge. You can have up to 128 registers of 2048 bits, which is huge. So if you don't want all guests to access this, and you want the integrator to have a full control saying, this is important in my hardware, I want this guest to be able to use it, but this guest should not.
Yeah, of course.
So that's why we need a configuration feature. Now, how we do this in the Pixel for now, and we did not discuss that in any way.
Okay.
It's might be a bit set, or I don't know. We did not discuss this, but we will have to provide a way from the configuration to say this guest can use it.
There is no question about that. The question was just how it would be represented in a guest config file.
We don't know for that's not the
on x86 we have the single CPU ID equals, which then basically enumerates everything you want to expose or hide.
The point is the CPU ID has another meaning on ARM, and we should not mislead the user.
And I don't mean you to use CPU ID equal, but I would not recommend that you have an SVE equal and a pack equal.
I kind of think that for those of stuff we should have something like CPU feature equal and a list of stuff that you can activate or not. The general problem we have in this is we will need a way for the configuration scheme to know if this is supported in hardware, and for some of those features, we will not want .0 to use it. That means we will need something as an information that's a bit set of what is supported with hardware, so that's a bit set of what features you can allow a guest to use or not from the configuration point of view, so that it's filtered out, and then a way for each guest to say, I want to use SV and PTI, but not NT.
So do you
this part, we have not, we did not even started on the implementation.
Yeah, exactly.
Do you have pre-existing features which you already enable or disable for guests, including .0 potentially?
Not at this stage, not at this.
Okay, so there's really something new that you need here.
Yeah, but there, we have some missing, so we need to have a broader discussion on this. For example, we have the same issue with FPU. Should we allow all guests to use the FPU? Yes or no? Right now, basically yes, but if they don't use it, so this should not be the case. We need to know so this is a more general question. How do you support features and how many of them do you need? Right now in Xen, we think that there are very small set of features, so we use names explicitly, but we need to have a more standard way to know how to support those kind of features, because more of those type of features will come into the future. But honestly, we identify the features that are on the ARMv9 CPUs that might make sense for Xen. And right now we investigated what do they mean for Xen, but we haven't started implementation. But
I would like to recommend that you take a look at the x86 side of this, where Andrew has introduced quite reasonable a mechanism to represent things as well as mask things from various entities.
Okay.
I don't think it would go as far as sharing code, because things are too different.
Yeah.
But the underlying model might be usable. It might even be reasonable to share things like sys controls or DOM controls that are involved in that process.
Right now, there are also, for example, there are lots of questions around SV. You might have hardware which supports 2048 bits, but for some reason we do want one guest to only use 128 bits because So we will probably need more than just a bit set.
Of course, yes.
For some stuff, we might need some integer arguments, etc. We need to have a broader view of what we need before we actually design something in this area. That's why we want to present those things so that people know. Because for stuff like LTE and etc., then there is a question of the keys.
Yeah.
How do you get the keys?
Yeah.
Who is the owner of this? Is it Xen? Is it the firmware? Is it? There are some huge questions around that we need to investigate deeply, because those are well, the main consequence is security. So you don't want to go straight to the implementation. We need to design this program. But the overhead of that, so right now we are just at the stage where we evaluate the cost and effort to port those features to Xen, and we will start the discussion with the community in the next months, or maybe during design sessions if some subjects are in particular interesting for the rest of the community. But you are right. And there is a huge question of confidence.
That you want to do a design session here, or is it too early for that? As a preliminary, maybe to see what options are there.
That was the initial goal. The problem is we are missing two of the ARM maintainers, which means that we can discuss this, but it might not have the wanted outcome, which is kind of a shame. But we are open to discuss if you want to.
Okay. So I think that's it for this presentation.
Just small question. Can you have as many Realm VMs as you wish? Is there some restrictions to how much Realm VM you can have on the platform?
Okay. Penny, did you hear the question?
It's about how many restricted Realm VMs.
Let's go to the other side. This one? Yes.
Is there some restrictions or number of Realm VM that you can have on your platform?
Actually, I don't know.
Actually, sorry, Penny, I can answer this question. Yeah. And for the Realm VM, actually, we don't have actual limitations for the number, and it uses the same VM ID as normal virtual machine. So the limitation is I think it's the same as the normal virtual machine. It depends on how many resources the host can provide.
Thank you. So there's no restrictions.
Yeah, basically yes. Okay. So yeah,
Thank you very much.
thank you everyone.